If you're settling in for lab rats, you're gonna want a clipboard probably.
That sounds good song.
Oh, come on. Alrighty, Liam, time to move yours. I'm gonna do it. Right, you can just, this time you can just say, say, no, don't share, we're doing it like Andrew, okay, with somebody.
I'll do that.
Alright. And Andrew, can you ensure that your gas is locked?
Yes. And then you turn in your light.
That's great. Okay, we're gonna get you five minutes. We're done. We got it. After this, you're gonna get one more mask in, and then you guys get hydrated, and then we're done.
All right. You said it right.
Hey, we're gonna start class in about 7 minutes. Then we've got 5 minutes to go, and then we give them time to mask and hydrate. Meanwhile, everybody else should be cleaned up as best as you can be, so this stuff.
Yes. No, God, that time is not hard.
Yeah.
It's for you too.
Hello.
Adios.
Bye.
Yeah.
Like, what about me? You got my name in your mouth, Dave? Okay.
They're back and stopped the whole game last year.
Oh, I think one more, maybe. Earlier this week.
It's a radioactive.
I said once. Like on purpose.
Yeah.
I don't remember which guy, because I don't know them very well, but it was rough, apparently.
You're so fun. I got the dirty one. I didn't even do anything.
Just, you know, race it.
Yeah. They're racing. Oh, that's all.
Yeah, so.
Today, last year.
This race was better.
Did you?
Okay.
I mean, I'm sure this race would be better,
What is that?
What?
Is that a dog toy? Art's understanding.
I'd be
What?
crying.
That is a dog toy.
And he told me that was the best.
It has legs moving on it. It says.
Stay down and down, sir.
Is it a dog toy?
Oh, that's dog toy, and they're cool because they have a red rubber inside. So if your dog is able to chew through that and get to the red rubber, they replace it for free, you just pay shipping. And honestly, being a tiny little beast, you wouldn't think could do damage, but he does amazing damage because he's a chewer. Like, that's his thing, like he loves to chew. And we've been through, that's our second one of those. But every other toy we found that they call it is not in step. Apparently, here we go.
Already.
But I don't know how I know that.
No matter
Oh,
what.
right,
So
ready?
don't ask.
Okay. Put your lid
I
right
don't know how I
here
know that feels like eggs.
and put your crucible right there. Get your mask, and then after you've had your mask, you rehydrate. You're all set. Alright. So I will put this in the email, but what we're gonna do is I'm gonna change the format of the assignment to an download upload. I'll be sure your answer sheet is there. You download the sheet. If you're the team captain, complete the sheet, upload the sheet. And you don't have to hand it in person that way, but I'll make that adjustment in your email and in your teacher ease. Okay, I'm passing out things now.
Next week, 1.4 up in town.
All right, good job. Make sure you enter that data. Where's Kate?
Why did the back is being clean on mine? I have bulky erasers.
Why is that yellow? Why is it, this is like yellow than mine?
Yeah. Erasers so white. Okay, this one actually kind of works.
This is your midterm study guide. You left go.
Why you guys making there?
Midterm study.
Yeah.
And bulky.
Where's Andrew?
Fine.
There you go. There you go. Very cool. All right, this is your midterm study guide. This is your midterm study guide. Yeah. Here.
I'm
There you go. Here you are. Yep. Midterm study guide.
It's really encouraging. Cause another quarter, I want to understand everything here, or like.
Not today, you won't, but you will eventually.
It's 59.
It's called Windows XP.
What is this?
Oh,
Alright, name it.
yeah, today.
I'm so funny.
And yeah. Drew, remind me that I need to drink another one. I don't know what. All right. We all good? Okay, you can do as minor amount of cleanup as possible because we need to get to class. So just Actually, y'all can just leave your stuff. I'll clean yours up, okay? Because we need to get to our lesson. We are running behind. We are running way behind. Yes.
How behind?
Oh, good. Excellent.
5 feet.
No, not.
So.
That's maybe
This is my
Two
Sit
cards.
on the couch. Not on the couch. Sit on the chair.
It's over there already.
Yeah, this is cool. This is a full couch.
All right, so just to review, I'm gonna put that in the email, so check the email. But the lab 10 assignment, let him sit. The lab 10 assignment in Teacher Ease will be a download upload. I will include the answer sheet. Lab team captains need to go ahead and complete it, upload it, use the average data from the Google Sheet. So everybody be sure that you get your average, your data in that Google Sheet by today. Like get it in there tonight if it's not already in there so that everybody can work on their lab. If some team doesn't put their data in, we're not gonna have an average. If they don't put their data in till like, Monday night, that's gonna cause a problem for everybody. So don't be that guy. There are only 4 of you, so we'll know who you are. All right, let's roll since we're now sufficiently behind, but that's a longer lab, so. So today we're gonna talk about Avogadro's number, molar conversions. If you don't have a clipboard, you may want one. Bring some over to the counter.
Where's the marker?
They're back there at that table. You guys wanna be dressed? Back there. All right. You can always work on paper, just sometimes people prefer I'm sorry, yeah, right, there's some at the back table too, and yeah. Dry erase markers back there at the. Yep. All right, so we're gonna start. We're gonna start with the video on Avogadro's number, what it is, and how big is a mole. Yay, no ad. I love it.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. A small furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your ant's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, just about anything extremely small. Have you ever wondered how many atoms there are in the universe or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you had equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Fortunately, Avogadro died in 1856. Now, the thing is that the amount of particles in even small samples is tremendous. For example, you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectrillion gas particles. That is, you have 6 with 23 zeros after it, particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particle. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind. Avogadro was the first one to come up with this idea. Scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 42 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it. The story of the mole, Avogadro, basketball, and how to buy salami at the grocery store.
So I like the fuzzy moles, so I'm wearing the fuzzy moles today. In case you didn't catch them, I've got moles all over me. Ah, all right. So Avogadro's number. What's the number? Everybody, you heard it. What is it? Right. 6.02 times 10 to the 23rd. It is the number of units that can be atoms, ions, molecules, formula units in a mole of any substance. Okay. So you're going to see my little guy is going to come through here in like a little mole animation. He's cute. So there's your number. There's our mole, and he's going to be popping up almost every slide. So this is our number that we use. We don't even bother with the second two. We just say 6.02 times 10 to the 23rd. That's what we work with, all right? Number of units. It's a counting unit, okay? So it's used to convert number of moles to a number of particles. You can do moles to particles, right? You can also do particles to moles, okay? You can go back and forth. Great, so conversion, it's a counting unit. Conversions between mole and mass require what we call molar mass. All right, so the molar mass of one atom of an element equals the number of grams numerically equal to the atomic mass unit. Don't get lost, we're good, okay? I know you're like, what? So, what is the molar mass of carbon? All right, here's carbon. It's number 6, but its mass is 12.011 AMUs, which means that it is 12 grams per mole. That's easy, right? That's easy. So what's the molar mass? If carbon is 12, what's the molar mass of iron?
28, 26.
Can anybody see it? It's like 55.8, so 56. How about what's the molar mass of potassium? You see it?
20.
39. What's the molar mass of oxygen?
15.
Yeah, 16, 15.99. What's the molar mass of argon? 39.9, so 40. All right, that's not hard, right? That's not hard. So how do we use this stuff? We just said, what's the molar mass of oxygen? So again, if carbon is 12, oxygen is going to be what? 16. All right, see how it works? That's not hard, right? Now we can use this
to come out with what's going to be the molar mass, for example, of carbon dioxide. All right, so there's carbon dioxide. It is carbon plus oxygen plus oxygen. Do we all agree on that? CO2. So we have 12 grams per mole plus 16 grams per mole plus 16 grams per mole gives us what? Anybody? Can you do it? What is it? 44? There you go. 44 grams per mole. Molar mass of carbon dioxide. Easy. That was easy, right? That was not crazy. Everybody's like, oh no, she gave us clipboards. I'm going to cry. All right. So now we can figure out our relative atomic mass and chemical formulas. And this is all because we have our friendly little mole. So an element's average atomic mass is going to be derived from the average mass of the isotopes weighted by the percent of their abundance in nature. Okay. We talk about atomic mass, right? So, for example, the atomic mass of nitrogen is 14.0064. All right, so that is the mass of the protons and the neutrons added together. But there's something called an average atomic mass. And what that takes into account is the isotopes in nature and how abundant they are. Some, like carbon is a great example. Carbon has a lot of isotopes, and some are more common than others. And we're able to get an average from that, and that gives us our average atomic mass. All right, you following so far? Not hard, right? So a chemical formula reveals the composition of a substance. What was the chemical formula of the substance you used in lab today? Copper sulfate. What was the chemical formula?
CuSO4.
CuSO4. Okay, there you go. CuSO4. So the subscripts in a formula denote the number of elements or molecules if it's in parentheses, right? We know this. And you can use a chemical formula to calculate molar mass. All right, so water. Let's do this one together. You can use your little clipboard if you want. H2O. It is 2 hydrogens and 1 oxygen. Do we all agree?
Yeah.
All right. See if we can come up with our molar mass for water. Give everybody a minute. If you need to write it down, write it down. If you don't, don't. And if you remember from the TEDx, the man actually gave the number for this one. All right, so got a little less than a gram, little less than a gram. Do you have an answer for it, Xander? What do you think? What's your molar mass for this molecule? 18, he says. And you put those together, you're going to get 2, 16, 18. Got it. Good. And in the video, he said something about 18 grams of water, which is the same as 18. What's the volume? Milliliters. 18 grams is the same as 18 milliliters of water, right? All right, we're following along. So there's your mole. Again. All right, now let's try iron 3 sulfate, or what we call ferric sulfate. Now, what does it mean when you have the parentheses and the subscript? What does that mean, Jordan?
There's 3 of that molecule.
3 of that molecule. So we have 3 sulfates. Do we see that? Okay, so this one's multi-step. I'm going to give you guys a few minutes and see if you can figure it out. Iron, I will tell you from over here, iron is about 6. And sulfur is about 32. And oxygen we already did, it's about 16. Jeez. All right. We still working or does anybody have an answer? Still working? Okay, Xander's got an answer. You hush. You don't need to come out. You're fine. Yusuf's got an answer. Everybody else is still working. Okay, let's work through our first step. So we're gonna have 2 irons. And then we're gonna have sulfate, which is SO4. Do we all agree with that? And then how many sulfates do we have? 3 of those. So we're gonna have 56 and 56, 32, 16, 16, 16, right? 16, one more. But we're gonna have that times 3. So we add our 56, 56, we get 112 for the iron. The sulfate is gonna give us 32 plus 64, which again, now we're gonna come down here. Now we got 96 times 3. And now we got 228. Does everybody follow that? Okay, kind of makes sense. All right, so there is our molar mass for ferric sulfate, 340 grams per mole. Did anybody get it? You got it? Yusuf got it? Okay, 340 grams per mole. All right, good. Good deal. There's our little mold again. All right, now this is what's important for you to understand because this is part of the lab. This is what you're going to be answering in your lab. So formulas and percentage composition. This is what you were doing today, whether or not you realized it. So percentage composition gives the relative contribution of each element to the total mass of one molecule or formula unit. If I put 2 apples and 3 lemons on the scale, and I got a total mass, okay, and say my lemons and apples, my lemons are exactly the same mass. My 2 lemons are identical in mass, and or 3 lemons are identical in mass, each one of them, and my apples, my 2 apples are identical in mass. I need to know how much is 1 apple. Okay, so you can figure that out if you work backwards, and you can figure out how much they would, if you know what each of them weighs on their own, you can figure out what they all weigh together, right? So that's what we're doing. So here's water. We just did water. Okay, we figured out what our molar mass is, right? It's 18 grams per mole. Does everybody agree? That's what we found for water, right? Okay, so percent composition by mass. That's what you're going to do today for lab. So basically, it's the molar mass of the element times the number of atoms divided by the molar mass of the compound. So times 100, obviously, you're looking for percent. So water's percent composition by mass of hydrogen. So how do we do that? We know that hydrogen is 1 gram per mole, and there's 2 hydrogens in water molecule. Does everybody agree with that? And the total molar mass of a water molecule is 18 grams per mole. So we know that water is making up 2 grams of that 18 grams. So when you divide it, you get 0.11 grams per mole. And if you multiply by 100 to give it a percentage, you're going to have 11%. Okay? Does everybody follow that? Yeah.
The like 2 divided by 18 is 1 by 9.
I mean, if you want to, sure. You can reduce it further if you need to. But you can do that calculation from there. That's what a calculator's for, 2 divided by 18. I mean, you can do that longhand if you want, but you don't have to. All right, so then Water's composition of hydrogen by mass is 11%. So what do we do then for oxygen? All right, I'll give you a second to try and figure that out. I'll put this back up. That's what we're doing. So molar mass of water is 18 grams. And you remember that hydrogen is about, I'm sorry, that, what did I say? Not hydrogen, oxygen. Wait, where was I? Where was I? Okay, oxygen. So we need to know what is water's percentage composition by mass of oxygen. Oxygen's molar mass is 16 grams per mole. Okay, see if you can tell me what's the percentage going to be. So the molar mass of the element is 16 times the number of atoms is only 1, divided by your molar mass of your compound, which we know is 18 grams per mole. You get something, James? What'd you get? What'd you get? 88.8. Okay, now here's the other thing. You got 16 divided by 18, 89, so 88.8. Now, what number did we get for hydrogen? What was the percentage we got? 11. And what for this? 89. In order to have whole, percent is part of 100. Okay, percent, part of 100. What number do we need to have whole here? 100. Is 11 plus 89 100? Hey, you did it. There you go, right? That's not that hard. That's not that hard. You should be able to add up your different percent composition for different atoms, and you should come close to about 100 when you get to the end. Now, if you're going to be rounding, it may be a little off, but you're looking for 100. So your 11 plus your 89 gives you 100. So water's composition by mass is, check your answer, 11% plus 89% is 100%. You did it, right? Not the end of the world. So there you go. All right. There's math, but it's not terrible math. It's not super scary math. So an empirical formula. Okay, this is something different. An empirical formula shows the elements and the smallest whole number ratio of atoms or ions that are present in a compound. Empirical formula. Okay, so how this works is you determine it by using that percent composition. Once you have your percent composition, you can figure out an empirical formula. Empirical means like experimental. It's kind of another way of saying this is based on our experimental data, this is the result we get. So if water's composition by mass is 11 grams per mole of hydrogen, 11 grams of hydrogen per mole of water, and 89 grams of oxygen per mole of water, then we can say 1 mole of the element divided by the mass of the element. All right. Here's a conversion factor. So you have moles over grams is the reciprocal of molar mass, which is grams over moles. Do we agree that grams over moles, the reciprocal would be moles over grams? Everybody knows what a reciprocal is, right? What's a reciprocal of 3/4? Say it. What's the reciprocal of 5/3? 3/5, right? Okay, so in this case, instead of moles over grams, it's grams over moles. So here's what we do with it. It's going to give us our moles of element. So if you have 11 grams of hydrogen, all right, and you have a mole of hydrogen divided by a gram, because we're trying to get rid of the grams. Again, it's conversion factors. Remember a while back we did conversion factors a little bit? You put the number that you're trying to get rid of on the bottom of whatever fraction or conversion factor you're using, because you're trying to get rid of that unit. So we're trying to get rid of grams. So we got rid of grams here, and all we're left with is moles. And so our answer is going to be 11 moles of hydrogen over 1, which is just 11 moles of hydrogen. All right, so what do you think it's going to be for oxygen? What do you think? Do what? 89 moles. What are you snickering at? Something has tickled him. So I don't even know what. Okay, so we have our 16 here. So this is where you gotta watch. You gotta watch. You gotta be So this is where you gotta be careful. So we need our grams here. Over here, our molar mass was just 1 because it's hydrogen. That's what this 1 is for. But here, our molar mass is 16. So if 1 mole of hydrogen over 1 gram of hydrogen, right? And here you've got 1 mole of oxygen over 16 grams, right? So you're using that reciprocal again. Reciprocal, I cannot talk today. So you're going to end up with 89 moles of oxygen divided by 16, which is your molar mass reciprocal we're using. You get 5.5625 moles, that should say oxygen. Whoopsie. No, I caught it. It's not a brownie point if I catch it, dude. Hold on, I just need to make it say, oh. Ah, fixed. Go through. Are y'all good back there? All right, so what is water's empirical formula then? All right, so 11 moles of hydrogen and 5.5625 moles of oxygen. All right. So the empirical formula, we have to look at the ratio. Okay, so here's where it gets important. You have to think about a little bit of rounding and a little bit of kind of like averaging and rounding. So if you have 11 moles of hydrogen and you have 5.562 moles of oxygen, what is the ratio of 11 to 5.5? 5.5, 5.6, somewhere in there. What's the ratio? What are you seeing? If you made it a fraction and you reduced it, what would you get? 11 to 5.5. What's the ratio there? The ratio is 11 to 5.5, but you can reduce that. What do you reduce it to? How many times? What do you call them? Hey, it clicked. It clicked for somebody. What'd you see? What did you see? There's 2 hydrogen and 1 oxygen, and the molar, here we're dealing with hydrogen, is 5.5. If I had 2 of these, would it be 11? Yeah, so if I have 1 of these, then that means there's 2, I have 1 of these, that means there's 2 of these, that's what your ratio is, 11 to 5.5. If you can reduce like 11 over 5.5, if you reduce that, you would get what? 2 over 1. So you're 2 hydrogen and you're 1 oxygen. Do you see that? Do you guys see that? So your ratio of 11 hydrogen to 5.6 roughly oxygen as a whole number ratio is going to be 2 to 1, right? 2 to 1 makes sense because water is H2O. Does everybody see that? I know it gets a little numbers. But you see that, right? Okay. How about, so chemical formulas can be used to calculate, percentage composition. What in the world is wrong with you people? Okay, whatever we're giggling about, get it under control because it's distracting. All right, and this stuff can be complicated to understand, and you're going to have to do it in your lab. Like, you're going to be doing these calculations in your lab, but with a much bigger molecule than water, right? So here's our water again. All right. First, determine the molar mass. So we determined that the molar mass of water was 18 grams per mole. Does everybody agree? 1 gram per mole, 1 gram per mole, 16 grams per mole. Add them up, you get 18 grams per mole. Everybody agrees, right? Okay. So then, next thing we're going to do is we are going to take the molar mass of the element, and the molar mass of the compound, which is what we just did a bit ago, times 100. And that's going to give you the percent of the element in the compound. Okay, so in this case, you're doing H, your hydrogen is 2 grams per mole. Do you agree that the hydrogen in water is 2 grams per mole? Not hydrogen on its own, the hydrogen in water. Do we agree? Okay, 2 grams per mole. And then total for water is 18. Do we agree? Okay, so if we make that a fraction, we get 2/18, which is, there's your 1/9 that you asked about before, which is your 0.11 times 100, which is going to give us 11%. What? 11% of water is made of what? Hydrogen. So then what's the percent of oxygen going to be? Yes. 89%. So water is 89% oxygen, but only 11% hydrogen. Even though there's 2 hydrogens in water, it's still far less percentage-wise than the oxygen. Why is that? Why? Oxygen's much bigger. Its mass is bigger. As an atom, it's bigger, right? It has multiple energy shells. It's considerably bigger. That's why. So then we had our 11% or 89%, and that's going to make sense again. All right. So this is our buddy, Amadeo again. All right. I did get ads on this one earlier, so I apologize before they start. I can't seem to make.
Something differently. than
yeah.
President Biden.
Yeah, I know. Everybody should have done different. Go away. Oh, I'm skipping the ad. There. Oh, what is it? Why is it all the way down there? Come on, gotta back it up. By the way, tomorrow is.
Incomprehensible.
Hold on.
Large number.
Stop talking.
It equals the number of particles in a mole of something. And in 2019, that was defined as exactly.
Okay, just so you know, tomorrow is 10/23, which is International Mole Day, and he's going to mention that in a second. But I thought I'd bring it up because it's actually tomorrow, so it's kind of cool that we're learning about moles today. All right.
6 times 10 to the 23rd particles. And as a chemistry teacher, I'm under a contractual obligation to love this number. I even got married on October 23rd, which is International Mole Day.
That's my kind of nerd.
I'm all in on Avogadro. Now, chemistry teachers love trying to use Avogadro's number in goofy conversions to show how big it is. But in the end, I don't think they're very helpful. There are lots of big numbers we can use in goofy conversions, and the story of Avogadro's number is so much more than the number itself. So if you really want to impress somebody with Avogadro's number, don't do conversions. Tell them stuff like this. Tell them that the scientific acceptance of atoms hinge on finding Avogadro's number. You see, starting back in ancient Greece, there were 2 camps when it came to the nature of matter. One camp, led by Aristotle, thought that matter was continuous, and you could continue to subdivide matter smaller and smaller onto infinity. The other camp, led by Democritus and friends, argued that you could only chop matter so far until it became uncuttable, atomos, as the Greeks called it. So for the next 2 millennia, the debate raged, but the atomists slowly started to pull ahead. Despite running up the score, Team Atom couldn't win the game. The problem was that no one could actually find an atom. What if atoms were so small that they were beyond experimental reach? To really establish atomic theory, scientists needed to find the absolute weight of atoms. And to do that, they needed Avogadro's number. Editorial note here, I'm going to stop using the term Avogadro's number for a while because this story starts at the beginning of the 19th century. And that honorary title would not be bestowed for another 100 years. So with that in mind, let's just call it secret number N for now. So if your friend isn't impressed yet, tell them that Avogadro's number was a powerful idea even before it was a number. In 1808, Dalton theorized that atoms of different elements had different and distinct relative weights. Dalton knew he couldn't find the actual absolute mass of atoms. They were much too small, but he had a hunch he could determine their relative masses, the mass of atoms compared to each other. So take, for instance, hydrogen and oxygen. Dalton thought that 1 gram of hydrogen would react with 7 grams of oxygen. So if those large laboratory piles of atoms had equivalent number of atoms, then the laboratory mass ratio should scale all the way down to the atomic level. So think about that. The relative mass of the atoms would be hydrogen 1 and oxygen 7. Take a look at the periodic table. Hydrogen's atomic mass is still right around 1. Dalton made a lot of mistakes for sure. If you look at the periodic table, the corrected relative masses are actually 1 to 16, not 1 to 7. But the big idea remains. We have an atomic mass in Daltons, and we have a laboratory mass in grams. It's the same number. It's the same reason why gold can be 19.3 grams per milliliter and 19.3 kilograms per liter. It's because the top and the bottom scale up by the same number, 1,000, so the ratio doesn't change. The number that connected those two realms of existence wasn't 1,000. It was astronomically larger. It was secret number n. But since it wasn't a direct part of the relationship, since it canceled out, scientists were doing just fine without knowing what secret number n really was. So if ratios aren't really your friend's thing, tell them that Avogadro never actually came up with Avogadro's number. In 1811, he was just an Italian physics professor with a different take on one of Gay-Lussac's discoveries. Gay-Lussac had noticed that when gases react together, they tend to do so in volumes which bear simple whole number ratios. Avogadro correctly took this to believe that equal volumes of any two gases under equal conditions contained equal numbers of molecules. Avogadro had a theory, never had a number. The actual number of molecules in those equal volumes was unknowable and frankly irrelevant as long as they were identical, as long as there was the same number of molecules in each. Now, unfortunately, Avogadro's contributions were largely ignored during his lifetime for a variety of reasons. He might have been completely forgotten, save the efforts of a fellow Italian named Stanislao Canizario. 4 years after Avogadro's death, Canizario would reintroduce the world to Avogadro's ideas in the waning hours of the world's first International Conference of Chemists, the extraordinary Karlsruhe Congress of 1860. Canizario used Avogadro's idea to lay out a convincing.
What? I was gonna ask you, where did it go? Hold on. I was gonna point out that, whoops, I was gonna point out that Canizario looks freakishly like, what actor would play him? It's easy. Well, come on, if you were to make a new movie with Canizario, would you not cast Tom Hanks? Is it just me?
I see it in the eyes.
Am I the only one that's like that shapeshifter Tom Hanks that was apparently back doing chemistry? Okay.
Avogadro looks in
Yes, that's always been my thought. And he probably was, because you
What
know,
was
they all
the
were.
basis of
I
our
don't know.
current established relative atomic weights? People were impressed. One of those new devotees was none other than Dmitry Mendeleev, who, inspired by the strength of Canizario's
See that one.
advocacy of
I love that.
Avogadro's idea, would publish the first true periodic table within a decade. One of our biggest failures when we talk about secret number n is to leave out all the unique and clever techniques used throughout history to try to determine its value. There have been lots of them over the centuries, at least 6.02 times 10 to the 0.5. But this video isn't going to get into all of those attempts. There were lots of famous names along the way: Faraday, Millikan, Planck, Einstein. That's right, Einstein. It was the 20th century and we still hadn't definitively verified the existence of atoms. Think about it. Einstein had to take a break from his theories of relativity to help push this across the finish line. Finally, in 1909, Jean-Baptiste Perrin experimentally validated Einstein's theories. It involved an ultramicroscope and some tiny colloidal spheres, but in the end, he would finally have observable phenomenon that validated the existence of atoms. Perrin had 3 different experimental techniques that each independently validated very similar values for secret number n. After that, it became intellectually indefensible to further deny the existence of atoms, and this would earn him a Nobel Prize in Physics in 1926. Perrin, in a truly class act, recommended that the value of no longer secret number n be henceforth known as Avogadro's number, in tribute to his critical early contributions. So when you bring up Avogadro's number, discuss how scientists were using it long before they ever found it. Mull over the fact that Avogadro's number was the secret conversion between the atomic and the macroscopic realms of existence, and that the fate of the atomic theory of matter rested on its discovery. Heck, name drop Einstein if you have to, but don't spend your time on the number. Avogadro didn't know it, and you probably don't need to know it either. Unless, of course, it's also your anniversary.
Okay, so Breaking Bad, yeah. All right, now, this was an intentionally shorter lesson because we kind of have to take our senior lab rat hats on and now kind of go back to our lab situation. All right, so first and foremost, I want to make sure we have all the data in the spreadsheet. Let me, hold on, fix this real quick. So have your stuff out. Okay, I'm gonna swap this to screen. Come on, do your thing. All right, now. Why are we doing that? Why are we doing that? Oh, come on. Here. Okay. All right, so let's fill this data in. So Ninja Turtles, what was your sample, crucible, and cover after your first heating? Okay, take you a minute. You take a second and grab that.
$61.6.
61.6. Okay, and then what did you get, Liam, after your second heating?
61.4.
Okay, that's good. That's a good number. All right, and then what was your constant mass then?
For the second heating, 61.4.
Oh, 4. It auto-filled, but I think it bumped it. Okay, let me hang on.
What was constant mass?
That should be your 61.4. What do we have? Oh, and then what do we have? Why is that there twice? I don't know why that's there twice. Constant. Copied it. No. Okay, I don't know why. We got an extra. I think it duplicated this somehow. Let me delete that. All right. What do we have for esteemed pyro intellectuals? What do you have for your sample, crucible, and cover after second heating? 60.3. So your constant mass is 60.3. And then what do we have over here? Armadillos for your second heating? Yeah.
58.5.
58.5. And then what do we have for constant mass is 58.5? 56.5. That's a big difference. It shouldn't be, these numbers shouldn't be quite so different on yours. But that's why we're averaging. Okay. I'm going to give you guys a second to, if you haven't already done this, to fix these here. Okay. I'm going to put your team names in because I haven't done it yet. So we got our data for esteemed pyromaniacs, but we need esteemed pyro intellectuals, Ninja Turtles, and armadillos. So when you have them, just holler, say your team name and what you're giving me. I think Ozzy needs to go out, so I'm gonna let him go. Ozzy, big stretch.
Ozzy. $5
Here? 5 grams?
Can be.
Okay. 5.0? Is that what we're saying? Okay. Where'd you get that? How are y'all getting these? Just making sure you know how you're doing them.
That's the initial one, right?
This is the mass of that's what you put in was 5. Did you put in 5? Okay, good. Ninja Turtles, what did you put in? What was your mass what was your mass of your sample that you put in your crucible to begin with? Was it right at 5 grams or was it 5 grams? Okay. And how about armadillos?
That should be fine.
I've been
Yeah,
4.9.
it's the initial.
It's never fully balanced, but we.
Okay, but it was close.
Good, pretty much right.
All right, armadillos, what was yours? Was it right at 5?
Yeah.
Okay. All right. So our average is gonna be 4.95 for that. All right, what's our mass for our anhydrous, Drew? 2.8. And what's our mass for our anhydrous, Liam?
2.8.
Yours is 2.8 as well? All right, and then armadillos, what was yours?
Yeah, that 3.
3.0? Okay,
Oh.
so just work out to, hold on. It's all right. Vicky. Wait. If he's going anywhere, he has to come to you, because we remember what happened. We don't want anybody going to him, because that was not good for him last time, so. All right, puppy, good boy. Okay, now you got this data. Now, here's what we're gonna do. I'm gonna play the remainder of the video that we started earlier, okay? And you guys are gonna watch it through to make sure you understand how you're gonna do the calculations, okay? Where is that? Oh, come on. Hang on, it's gonna be back to here. Move this out of the way. Ah, no, I just lost it. There you go. Whoop, got lost though. Okay, where is it going? It's gonna make me crazy. I hate it when it makes me nuts like that. Come on.
Camera's there.
Trying to send it back over, but it doesn't want to play. Okay, hang on, let me. Pause recording for